Alright, IGCSE Chemistry 0620. Now we are presented with Chapter 04, which pertains to electrochemistry. So we will be covering everything about electrochemistry in this lecture. Double underline that. Right. Simply speaking, diving into the world of electrochemistry, this is simply the combination of electricity and chemistry. So simply electricity and chemical substances. That's what we are focusing on here. Alright, so under electrochemistry, the first main subtopic that we have to properly dive into would be electrolysis. So electrolysis, or this can also be pronounced as electrolysis. It doesn't really matter. I'm pretty sure there is a proper pronunciation. It's either electrolysis or electrolysis. Doesn't really matter. So I doubt that pronunciation will hold you back if you know the content properly. So don't focus on that too much. Let us learn what electrolysis is all about. Right, so under electrolysis, the first and foremost thing that I want you to focus on would be the formal definition that I am about to assign to this term. Whenever you see a DEF with a bracket, so just so you know, this is going to be a formal definition which you have to memorize. Okay, formal definitions are one of those that you will simply memorize. All right. So what exactly would be the formal definition for electrolysis? And why in the world would formal definitions be required? Simply speaking, questions will straightforwardly ask you, define electrolysis, or give the definition of electrolysis, or describe what is meant by electrolysis. So at those moments, so typically questions are going to be like about perhaps 2 marks or maybe maximum 3 marks. So in those scenarios, you really have to understand what to say. So to make sure that you do not lose marks at all. Simply, this is what you have to know, the definition. So what exactly would the formal definition of electrolysis look like? Before going into detail on that, let me zoom in and focus in on this. What is this? That's simply the term, right? Electrolysis or electrolysis. So actually this word is built in a certain way. Electro has its own term and lysis has its own term. Simply speaking, electro is simply just as it sounds. So regarding electricity or something related to electricity. Lysis, the term lysis is actually a meaning for the term breakdown. Breakdown. So simply electro refers to electricity. Okay, write that down. Electricity. This, so lysis, simply Lysis, lysis refers to the breakdown. So when you simply put together these things, or when you simply put 2 and 2 together, you will reach something like this. So pay very close attention to this definition that I'm about to share with you. Let me actually pick a proper color before that. Where do I have my colors? Okay, right. Simply, electrolysis or electrolysis, doesn't really matter once again. Electrolysis is the breakdown. So we just said that it's the breakdown, right? So it's going to be the breakdown. So, but a better term for breakdown in chemistry is going to be this: decomposition. Electrolysis is simply the decomposition of an ionic compound. Don't try to focus too much on this ionic compound thing. You know ionic compounds right now, so you've done chapters 1 and 2, 1, 2 and 3, so you are introduced to ionic compounds there, so don't stress too much about that. Honestly, even if you don't have that introduction, it'll be fine. Once we discuss examples, you'll see why we talk specifically about ionic compounds. So simply the decomposition of an ionic compound. When that compound is in its molten or aqueous states. Interesting. Very interesting. Molten or aqueous state. Simply to break the ice, I'll tell you that molten is melted and aqueous is dissolved in water. Okay, more on them on detail later. So when in molten or aqueous states, so what's the most important thing? How do we break them down? How do we decompose them? Using electricity. So by the passage, by the passing or by the passage of electricity through it. You can also say electric current, but you can just keep it short. Electricity through it. And also, if you really like to summarize things and you are you're really good at like breaking things down into smaller pieces, just make sure that everything here is actually included, all the keywords. So decomposition, then you've got that they have to be in their molten or aqueous states, and electricity. So those are the keywords. So if you were to shrink this definition down, make sure you keep all of this. So you simply keep all of this information as is and shrink it down. Okay. All right. So that will be the formal definition of electrolysis. The decomposition of an ionic compound when in molten or aqueous state by the passage of electricity through it. Once we are through with that definition, enter the world of electrolytic cells. Enter the world of what? Electrolytic cells. So simply electrolytic cell. We'll be talking about an electrolytic cell. So if you've never heard of this term before, don't worry. You're in good hands. I'll explain to you in the best way I possibly can. So I'm going to take my time and draw a nice little simple, very basic electrolytic cell for you. Alright. Simply, you need some kind of content. You need some kind of content. It's actually very bad at that side. Jeez. Okay. Oh, that's better. Right, some kind of container. It doesn't really matter what type it does, but in this particular scenario, it does not. So inside them, you're gonna have simply 1 and 2. So two things that look like that, and then filled with something. Something, we'll get to that something later. And then followingly, you can see that these two things are actually connected, to a cell, something that looks like a cell, right? You see positive, negative, something that looks like a cell. Okay, simply put, this is your electrolytic cell. Nothing more, nothing less. Of course, the labels are missing, but this is simply your electrolytic cell. This is simply your electrolytic cell. Now let's get to labels. Very simple, okay? So these things, this and this together, they are actually known as electrodes. Do you see this? Electrodes together, okay? Electrodes. And then here, inside this container or basin or something, you will find your, we call this the electrolyte. light. Do you see how all these words follow the electro scenario? Yeah, electrolyte. And then here, this is simply your cell. No, I'll just label it as the cell. Cell. Boom. All right. And then this is where things get more specific, to be honest. So I'm gonna pick a nice bright yellow, right? So do you see how the positive terminal of this cell is connected to this particular electrode? Do you see that? Do you see how this positive terminal of this electrode is connected to this cell? That would make this the anode. Pronounce it again. Anode. Do you see? Anode. ANODE. In a similar fashion, you will see that this negative end of the battery or the cell is connected to this electrode. See, remember, both of them together, they're known as electrodes. Then what do we call this? This guy is known as the cathode. So whenever you are actually connected to the negative end, you are referred to as the cathode. You are referred to as the cathode. And then another fun thing about these electrodes, so anodes, cathodes, electrodes, right? So another fun thing about these electrodes is that these electrodes can actually be, so they can be inert, inert, or they can be active. What does that mean? Thank God, the definition, more like the idea, is very straightforward. If the electrodes are inert, I'll pick my laser pointer. If the electrodes are actually inert, they will not take part in the reaction, meaning they will not simply break down into this electrolyte or just interfere with anything or change any chemical reactions or change the product or anything like that. They won't. But if they are active, but if those electrodes are actually active, they will break down into the electrolyte, they will take part in reactions, they will just interfere with reactions, change the product and all of that. Okay, so that's simply the basic definition of inert and active. Don't worry, you will come across like many inert and active electrodes as we go along the course. Just for like nice little starters, I'll mention that the most common inert electrodes that you have to know are carbon. Okay, just so you know, whenever you see that carbon is used as an electrode, you have to know that it's inert. Okay, so carbon or graphite, actually sometimes this is referred to as graphite. You know that graphite and carbon, they're the same thing, right? They are simply the same thing. Graphite is made out of carbon. So carbon or graphite, inert electrodes. And then what about active electrodes? What could they possibly be? The most common, the most annoying active electrode is actually copper. It's actually copper. Okay, so more honestly, there are more examples, but for this particular time, like for now, those are what I would actually advise that you know. So simply a recap, this is the electrolytic cell composed of the two electrodes, the electrolyte and the cell. Come again, show well. Electrodes, the electrolyte and the cell. And the cell. Alright, so that is all about the electrolytic cell. Oh, and one more thing, sorry, I forgot. So here now I told you that whenever we talk about the electrolyte has to be in two states, no? It can be a melted version of that, so the melted version of any ionic compound, or it can be an aqueous form of any ionic compound. Aqueous form of any ionic compound. So simply just drop down some brackets and mention that the electrolyte has to be or aqueous. Okay, simply that's it. Final thing. Right, now the next thing that your syllabus actually requires that you really focus on is this. The movement of current. That's a very precise of current in electrolysis. The movement of current in electrolysis. So as you know, there would actually be specific ways in which current can actually flow. So more precisely, specific ways in which the electrons can flow. What am I talking about? Weird, right? So simply speaking, so let me pick a bigger pen, right? As you know, this would be how current or electrons, so E dot, so E minus for electrons flow in this following manner. Okay, so through a solid, they flow in one way, and through liquids, current flows in one certain way. What are these certain ways? Now, this might be very confusing because this might kind of be new, but I'm pretty sure you kind of know this already. So here, when electrons flow through a solid, when current flows through a solid, the free electrons in that solid will carry this current. So the best example that I can provide you with is a metal. Metals have loads and loads and loads of free electrons. Metals have what? Loads and loads and loads of free electrons. So simply speaking, whenever current flows through a metal, all these free electrons will simply carry that current. So through a solid, you would have to have free electrons. Another term for free electrons would be mobile electrons. So we know that to be mobile is to be able to move. Simply your mobile phone, you can move it everywhere. That's why it's not known as a telephone. So we had telephones, now we have mobile phones, smartphones, and all that stuff. So the reason being they can be moved everywhere. So yet another more scientific term for free would be this. This is a stretch, so bite your tongue, I guess. Delocalized electrons. So you would have to have delocalized electrons to actually allow current to pass through a solid substance. Best example, metal. Okay, and what I want you to really focus on is this term. So it's all right if you say free electrons in an answer. It's all right if you say mobile electrons in an answer. You will get marks. That if you really want to shine through into the examiner's eyes, I really suggest that you use the term delocalized electrons. Okay, honestly, I'm not going into too much detail on this here because this is not really where this belongs. This belongs in a certain different chapter, so simply speaking metals. So this will be done under more detail under that particular topic. Okay, so here you just have to know that this is what happens here. And then what about the liquid? What in the world is the liquid here? It's simply the electrolyte. Remember, when you melt something it becomes a liquid, or when something is dissolved in water it's simply a liquid. Okay, so simply the circuit has to be completed. No? What circuit, you might ask? Not to worry, we'll get to that. So through a solid, this is what happens. Free or delocalized electrons. Then what about through a liquid? You would have to have free ions. What? Free ions. What in the world do we mean by free ions? So you know those things like Na plus, Cl minus, these are referred to as ions, not ions, okay? That's a completely different thing. Ions is a completely different thing. Ions is a completely different thing. All right. So this is what you mean by free ions. Now, being a chemical student, being a chemistry student, like I said before, a couple seconds ago, I suppose, I really don't want you to use the word free. Whenever something can move, I want you to use the term delocalized. Delocalized. What? You would have to have delocalized ions. You would have to have delocalized ions. That is how this moves. That is how current, that is how this electricity actually moves through this entire circuit. So you see, it has to be an entire circuit, simply like this. One whole full circuit. Right, delocalized ions. So now to really push this in the cell, what cell? This cell, and along with the electrodes, so in the cell and the electrodes. So simply speaking, what do the cell and electrodes belong to? Are they solids? Are they liquids? This is a metal bar, this is a metal bar, these are wires, and the cell is simply made out of metals as well. So in the cell as well as the electrodes, current, remember we're talking about the current, so current flows by electrons, not just electrons, delocalized electrons. Okay, current flows by delocalized electrons. Then what about the electrolyte then? Now you obviously, if you've been listening, you will know that the electrolyte is a liquid, so obviously current flow by ions, not just ions, once again, delocalized ions, delocalized electrons, delocalized ions. Now this really opens us up to yet another concept under electrochemistry. What is that? Now remember how I told you when we first started that whenever we do electrolysis, whatever compound it is or whatever ionic compound it has to be in its molten or aqueous states. Has to be in its molten or aqueous states. Why? You can be answered now. Now you have enough information to understand why. So let's see. Let's simply see. Let me pick a pretty blue color. Right. So in the electrolyte, it's either molten or aqueous, no? So when that's the case, ions can move. Ions can move. So it's like this. So if I take an example ionic compound, one of the most famous and nefarious ionic compounds are salt, sodium chloride, NaCl, right? So NaCl is just a white little grain or powder, something like that. So will the ions inside this be able to move? No, not really. They are fixed in place. They are fixed in place. You see, sodium is highly bonded to chlorine. They can't move. They are not delocalized. They're not delocalized ions. They are localized ions, not delocalized. They are localized ions. So then how exactly are we going to allow? So if you were to just put solid, here, look here. If you were to put solid sodium chloride, so simply if you were to put just, salt into this, you can never do electrolysis. Why? You have to have delocalized ions to allow the current to actually flow. So what do we do here? We have two options. We can melt this sodium chloride. So this is solid sodium chloride. We can melt this, or we can mix this with water. We all know that when salt is mixed with water, it disappears. Why does it disappear? Because it simply dissociates into its ion. So when you do this is what happens. You get the Na plus ion separate and the Cl minus ion separate. Two separate ions. Now they are no longer bonded to each other. They are free to go wherever you want. They are free to go wherever you want. So I'm just going to put everything into writing to make sure that you really understand. So simply, that is why you need to make it melted. So molten, okay, melted means molten, or aqueous, so dissolved in water. So it is only then that current can flow in solid states. No ions can move as they are fixed in place. In the solid state of any ionic compounds, ions can move. They are fixed in place. That is simply what I'm trying to say. Okay, ions can move. They are simply fixed, not foxed. Geez, sorry, fixed in place. That is the reason why you have to have molten or aqueous compounds whenever you are actually doing electrolysis. Whenever you are actually doing electrolysis. All right, so with that, we can move on to just sketch the electron flow pathway. What? To sketch the electron flow pathway. What? Electron flow pathway. I'm gonna use this red color actually. Can I use that? Yeah, I can use that. So this, I don't know, brightish pinkish color to actually denote that. So let's just see how this is going to pan out, right? So when we look at one single electron, what charge does an electron have? Obviously minus, right? So that would mean that the electron is negatively charged. Electron is negatively charged. And one of the most common laws in electricity is that opposites attract. So opposite, more like opposite charges attract. Say opposite charges. So opposite charges attract. Like charges repel, right? So opposite charges attract. Like charges repel. So using that, we'll just see what would ideally happen to an electron. So here, zooming in, we have the negative end of an electron. Sorry, the negative end of the cell. Negative end of the cell. So simply, electrons will be repelled here, right? Electrons will be repelled here. So when electrons are actually, where'd my drawing go? are repelled, this will be the scenario. Hmm. Electrons move. Electrons, okay, pay very close attention to what I'm saying. This is how electrons move. And boom, problem. Remember, electrons carry current only in solid substances. Now you're met with a liquid. How would you sort this out? Simply in the electrolyte, you will find what? You will find ions. You'll find ions. So now that that current is going to be carried by ions onto the other electrode, and then simply once again back to solid. No? So it will be the electrons that carry this charge back. Do you see? It's a closed loop. So simply this color would represent electron flow. The pink represents the ionic flow, the ionic flow. All right, so that is the final basic thing regarding all this electricity and the electron flow and the basics of electrolysis is over with that. So you've got electrolytic cells, and this is how current actually moves in electrolysis, and we talked about the electron flow pathway. We talked about the electron flow pathway. So that would simply conclude subtopic 1. So what was subtopic 1? Simply electrolysis, all the basics and la-di-da and all of that stuff. So breaking free of all of that, now we can introduce ourselves to the actual process. So honestly speaking, what really matters, what the process is all about, what we do and all of that stuff. So take down the next subtopic that you'd have to. Carrying electrolysis. What happened to my Y? Never mind. Carrying electrolysis out. Carrying electrolysis out. What do I mean by carrying electrolysis out? Simply doing electrolysis. We're going to see how electrolysis is done, how everything behaves. So just to refabricate everything that we learned before, now we clearly know that you can electrolyze, straightforward, electrolyze molten stuff. So you can electrolyze a molten compound. Molten is simply melted, okay? No big deal. Molten compound. Or you can electrolyze an aqueous compound. You can electrolyze an aqueous compound. Boom. Okay? So that's what you can do. You can electrolyze a molten compound or an aqueous compound. So to really suture this into your mind, we're going to be starting off with a molten compound. Okay, so example 1, we'll be talking about molten compounds. Okay, we will be simply electrolyzing a molten compound. What, you might ask? What are we gonna electrolyze? Okay, we will be electrolyzing. This is one of the best examples to actually electrolyze molten, obviously, right? Molten PbBr2. What is that? PbBr2 is simply lead, so lead bromide. Simply lead bromide. We'll be electrolyzing lead bromide. Let's see. So this is the first example that I'll be explaining. Okay, so pay very close attention to what I do, and I want you to just follow things as I do in any electrolysis question so that you won't ever be confused when we come across one of these things, or when you come across one of these things. So simply I'm going to draw a very simple electrolytic cell here. just to make sure that you will really understand all the ion movements and all of that stuff. But as you get better and better at this, your diagrams don't really have to be this detailed to figure out the ions. Okay, I'll just teach you shortcuts going through. Right, okay, so obviously it's going to be connected to a negative answer, positive, negative. So now I want you to think in your minds, what is this? That is the anode. What is this? That is the anode as well. Wrong. An electrolytic cell can never have two anodes. What do you call that? That is known as the cathode. So now, here's the important thing. What are we electrolyzing? What is our electrolyte going to be composed of? What is our electrolyte going to have? PbBr2. Just PbBr2. Why is it just PbBr2? Because it's only melted lead. Nothing more, nothing less. Only melted lead. So we will simply be putting molten PbBr2 or molten lead bromide to this. Molten lead bromide into this. So what should we do in electrolysis? This is the first step. This is the first step. You figure out the ions. You figure out the ions. What exactly are the ions? Where it's literally right there in front of you. We have the lead ion and we have the bromide ion. So how do we actually know what this is? So I know for a fact that lead is actually Pb2 plus. So that's the ion along with its ionic charge. Okay, ions always have charges. Okay, they will never be like this. That's the lead atom. That's the lead ion. This is the chlorine atom. This is the chlorine ion. Right, so ions will always have charges. And how do you know these charges? How do we know what these charges are? That is actually a completely different chapter. That does not belong here. So ions and their ionic charges belong to a different chapter. So that is where you'll be learning about those things. That is simply where you will be learning about the charges on them. So singular atoms, singular ions, and polyatomic ions. Don't worry, those are available as well. And then the bromide ion, Br1 minus. So now we have the lead 2 plus and the Br minus. Okay, so simply we broke things down into ions. Simply we broke things down into ions. And don't worry, this example will be very kind of slow. You might get bored and you might want to leave. But don't worry, because since this is the first one, I really have to explain that. And now, this actually presents me with one of the most wonderful opportunities to talk about inert electrodes. Remember, inert electrode. So here, in this case, in this case, we are using inert electrode. So what can the electrodes possibly be made out of? Carbon, right? Or graphite. Same thing, by the way. Inert electrode. So they, once again, what's the most important thing? They do not you see what exactly happens when they do. Okay, you will see what exactly would happen when they do take part in the reaction. Further questions coming up, so don't worry. So they don't take part in the reaction. So you can completely forget them. You can completely forget them. Right. Now take a good look at this picture. Take it down on your own. Make sure you do that. Don't just stare at the canvas blankly. Have a book, have a paper, have a pencil, have a pen, do things, then you'll see. Okay, so what's the next thing? The next thing will be to refurbish about electrolysis. What was electrolysis? Simply the breakdown of something by the passage of electricity through it. So now we've simply passed electricity through lead bromide, molten lead bromide, and now that's broken down into ions. So after it's actually broken down into ions, they go and stick to the electrodes. They go and stick to the electrodes. That would look something like this. So once again, going back to charge rules of charges, we know that opposites attract, like charges repel. So simply Pb2 plus is a positively charged ion. It's a positively charged ion. This will simply go and bind to the negative cathode. The negative cathode. What do we mean by binding to the negative cathode? Zooming in, it's like this. This lead, these many, we're not just gonna have one lead loop 2 plus ion. We are going to have a huge amount because we're putting a lot of lead bromide. So what exactly happens is this lead 2 plus ion goes near the negative electrode. Why? Because the negative electrode is negatively charged. The lead ion itself is positively charged, so it's simply going to go and stick to the surrounding like this of the electrode. Okay, so after some time you will honestly observe some changes. So in this case, I believe lead will be like a like a whitish solid depositing around the cathode like this. Okay, so that's simply what happens. So it's this exact same thing with bromide, with the bromide ion. So the bromide ion is negatively charged, opposites attract, so it'll simply go to the anode. It'll simply go to the anode. Boom. Same deal, no difference, honestly. It's like this. No, so the bromide ion. I'm gonna pick a very suitable bromine color. Okay, this will be good. Right, so the bromide ion. Now, will the bromide ion go and stick like this? Not really, because when the bromide ion is converted, you get bromine. Bromine will not stick like this. Bromine is a gas. It'll just simply bubble off into the atmosphere. Lead is not a gas, no, so that's why it really sticks. So depending on the nature of the compound, depending on the nature of the element, depending on the nature of the element, you can observe different behavior. So actually, if the examiner were to ask you, what would you see? What do you see? So that's an eye, by the way, that's your eye. So what exactly do you see here? You're going to be saying brown color gas evolving, brown color gas evolving. Don't worry about those things. You have a preset, set of observations that you have to know, which I will teach to you, so you don't have to worry about too much of that. I just want to introduce you to all the possibilities that you have. Right, so recap, briefing, what exactly happened. The lead 2 plus ion went to the cathode, the Br minus ion went to the anode. Now what do we have? Here we have lead depositing, here we have bromine evolving. So the next thing, perhaps the most important thing that you're tested on your exam, is electrolysis. I'm going to get rid of this electrolyte, okay, just so that I have space. The most important thing, wait, hold on, I need a color, right, yellow, would be, sorry about that, called half reactions. Electrolysis, half reactions. What exactly, or what in the world are half reactions? Half reactions are simply what is going on at each electrode. So simply speaking, how many half reactions should you have? Two, right? Because we have two electrodes. We typically start off with the anode reaction. So we will have our anode reaction. And then we will have our cathode reaction. So don't worry. Simply always remember what they're asking, what these reactions are depicting is what is going on there, nothing more. So you don't have to worry. Think I can use like a white color, right? So let's just look at the anode. Honestly, I'll just start off with the cathode reaction. It doesn't really matter where you start off, but I'm going to start off with the cathode reaction. So this is the cathode. What's going on at the cathode? What exactly is going on at the cathode? The lead 2 plus ion is going to the cathode and fixing that. So what exactly happens? Look here very closely. The lead 2 plus ion, okay, lead 2 plus ion becomes solid lead, right? So every single time in one of these reactions, the ion will be converted to the element, or the atom will be converted to lead. So lead 2 plus is converted to lead. So it's just going to stick to the outer side of this cathode. All right. Now this can't just happen like this. This can't just happen like this. I'm going to get to it in a second. Now just go back to the anode reaction. So what exactly is happening at the anode? Br minus is becoming what? What's the elemental form of the bromide ion? Bromine, right? It's bromine. So lead ion, lead, bromine. Is bromine Br? No, it's Br2, right? It's Br2. Bromine is Br2. These are diatomic molecules. Fluorine, chlorine, bromine, iodine. Those are diatomic, meaning they have two atoms to them. So then now this completely throws this off balance, and so to balance things, we put a 2 in front here. 2 Br minus. Okay, nothing fancy, just balancing. Right, now let's just look at how these things actually become like this. How? How? Simply, you have to talk about electrons. To make lead 2 plus into lead. So lead is 0. No? Any atom by itself is 0. These will be discussed under oxidation and reduction. Where's my eraser? Okay. So to get from plus 2 to 0, you have to minus 2. No? So that would be adding 2 electrons. So lead 2 plus 2 electrons becomes lead. Comes lead. And I actually mentioned, yeah, never mind. So lead. Okay. Here what happens? So 2 Br minus. So you can't do this here. No? That's not really how it works. It's not going to go backwards. So you have to balance things out. So that would be the 2 Br minuses losing 2 electrons. So they are simply losing 2 electrons. So you put it on the other side. You can do this, you know. You can do this. Look here. You can simply say minus 2 electrons and boom, right? You can do this, but you can do this, but this is not valid in chemistry. You can never subtract anything in an equation. You can only add. So when you take this to the other side, what happens? When you take things across the equal sign, basic mathematics, signs change. Signs become opposite. So Br2 plus 2 electrons. Plus 2 electrons. Honestly, writing half reactions, it's not that complicated. You just have to know oxidation and reduction like this, you know, simply electrons in electron involvement, how these things behave, and all of that. All right. So that would be the anode reaction, and that will be the cathode reaction. That will be the cathode reaction. So I'll just give you the state symbols for these things because it's important that you know what the state symbols for these things are as well. What do you mean by state symbols? Simply whether it's a solid, a liquid, a gas, or whether it's in its aqueous stage, meaning whether it's dissolved in what. Go down. Right, so Br minus. Any ion that is like this, we know it's in, sorry, it's in its aqueous state. Any ion. Now this is melted, I know, right? You can ideally represent this as being in its liquid form as well. Could say liquid, but typically when we represent ions, we say it's in its aqueous form. So AQ, right? So that applies for this as well. Lead 2 plus is in its aqueous form and like that. So bromine and okay, lead is a solid. Electrons, of course, they don't have a state. Like you don't have to write state symbols for them. What about bromine? Bromine is actually a liquid. Now, I previously mentioned that bromine is going to be a gas and it's just going to evolve out of the basin. Yes, that is true, but I actually kind of forgot that bromine is more of a liquid. So it's an orangish brown liquid, to be honest. My mistake. I apologize about that. Bromine is a gas. Bromine gas is very heavy and dense as well. Here, what you'll see is honestly like orangish brownish color liquid forming, and then you'll see a little bit of gas evolving. So yeah, so simply bromine will be a liquid. Okay, bromine will be a liquid. So those are simply the state symbols. And one more thing, one final thing that questions love to ask you is to, so now we have two reactions, no, anode reaction, cathode reaction. Questions will ask you which reaction is oxidation and which reaction is reduction. Confusing question, throws you off, problematic, everything in between, right? Don't worry about this too much. Oxidation and reduction will be covered properly under oxidation and reduction, obviously, the future chapters. But for now, what I want you to know is this. You know all those oil mills and stuff? So we call them oil rigs. So these oil rigs are what actually pulls, oil from the ground and rocks and everything onto the surface so that we can actually use them. Oil rigs. Okay, so now this simple mnemonic can serve you for life. Can serve you for life. Why oil rigs? Simply, this is the iteration. Oxidation is the loss. Oxidation is the loss. Loss of what? Loss of what? Oxidation is the loss of electrons. Sorry, oil rigs. Why did I say rigs? Oil rig only, okay? Reduction is the gain. Gain of what? Once again, we're talking about electrons. So how do we use this? This makes no sense, right? It's like this. So look here. Here, what is happening to the bromide ion? Okay, here, first look here. What is happening to the lead 2 plus? We are adding 2 electrons. We are adding 2 electrons. So are we losing electrons from the lead 2 plus or are we gaining? We are gaining. So we are gaining 2 electrons to the lead. So what is gain of electrons? Reduction. So this is the reduction reaction. So ultimately, if one is the reduction, the other will be the oxidation. To further confirm that, we'll just see here with oxidation should be the loss of electrons, and you can clearly see the Br minus is losing these extra electrons to become Br2, and boom, oxidation. This is the reduction reaction. This is the oxidation reaction. This is the oxidation reaction. Now we can do one more thing here. So I'll just move oil rig to the right side right over here. Okay. So we just wrote what? We wrote the half reactions, right? We wrote the half reactions, anode reaction and the cathode reaction. And we can do just one final thing. We can actually combine those half reactions to produce an overall equation, Okay. The only thing you really have to remember when it comes to an overall equation is that you have to ensure electrons are balanced first. Ensure electrons are balanced first. What do I mean by that? So now I'm just going to take these two half equations back down. First one, second one. So 2Br minus. Oh, sorry. 2Br minus. Where's my minus? Right, 2Br minus Br2 plus 2 electrons. And my second equation is simply this one, lead 2 plus 2 electrons, becoming lead. Step 1, ensure electrons are balanced. 2 electrons in the first equation, 2 electrons in the second equation. They are perfectly balanced. Now all you have to do is just combine the two equations. That would look something like this. So everything on the left side of these arrows go together. So 2Br minus from here plus lead 2 plus from here plus we have the 2 electrons from here. So done, done, done. So the arrows are combined as well. Now what do we have? Br2 here, lead here. The order doesn't really matter, so don't worry. And then finally 2 electrons. And typically, when you have same terms on both sides of an equation, you can cancel. We can cancel the electrons, you see? 2 electrons, 2 electrons. Simply just get rid of them. And then just work with what is remaining. So what do we have remaining? Boom. 2Br minus plus Bb2 plus gives you Br2 and lead. This is our final overall equation. This is our final overall equation that we achieved. Let me put in the state symbols. aqueous, any ion, remember, aqueous. Bromine is a liquid, lead is a solid, and that would be the final equation for the electrolysis of molten lead bromide. Now this was a very lengthy explanation of an example because this is the first thing. I really have to make sure that I get into your head. For the future examples will be very short and I'll show you tricks to actually do them. What you have to do is really get this into your mind, really focus on this, really write things down on this, and just make sure you're comfortable with writing half reactions, forming the overall equation, figuring out what ion goes where, and all of that. Okay, so just to check, so to really just check into your knowledge, I want you to do this. So this will be a self question. Of course, I will discuss the answers right here in this session as well. I want you to do this first of all on your own. So a self example. I want you to electrolyze. So on your own, I want you to electrolyze molten potassium chloride. If you don't know what potassium chloride is, KCl. This is just going to follow the exact same structure as this, because here we're once again electrolyzing a molten compound. Once again, we're electrolyzing a molten compound. What I want you to do is do this on your own first. It's alright if you make mistakes. Honestly, accept those mistakes. Don't try to like run away from those mistakes, otherwise you'll never learn. What I want you to do is really do uh, what am I talking about? Do this question on your own, and then in this session itself, I will discuss the answers, and then you can just double check, compare, and see where you went wrong. All right.